GPU parallelization. As explained in the previous section, in the RWDD approach, the behavior of each packet of charge is computed independently of the other charges. These processes being independent, the calculation task of the charge transport can be easily parallelized on a graphic processing unit, GPU, whose internal architecture is perfectly adapted to such a massive parallelism. Moreover, RWDD model needs to implement a random number generation procedure that is usually very time-consuming. If the random numbers are independent, this task can also be easily parallelized on GPU. These two characteristics of the RWDD model are expected to offer a considerable computation speed, since the number of parallelizable tasks in RWDD is relatively high. In this work, we use the CUDA programming framework proposed by NVIDIA, CUDA version 5.564b. Random numbers are generated using the CUDA Current random number generation library, Mersenne Twister, within the parallel kernels running on the GPU. Figure 3 illustrates this parallel implementation of the RWDDCPP code. For the purpose of this work, we separately tested the RWDD algorithm implemented in series on a CPU and in parallel on a GPU. Tests have been performed on a machine equipped with a 3.2 GHz Intel Core i5 and with a NVIDIA GeForce GTX 675MX, 960 threads at 600 MHz. Our results show that for the simulation of 100,000 charge packets with 1000 time steps, the speedup on GPU was 140 times with respect to the classical CPU implementation. Program flow for the parallel version of the RWDDCPP code. The main part is executed on the CPU, host, and the RWDD computational part is executed on the GPU, device. The code is also dynamically coupled with SPICE for circuit simulation within the transient event time domain. Reprinted with permission from Glorieux et al., copyright 2014, IEEE. Multiple node charge collection. Cartoon, at 5 different times after the ionizing particle impact, illustrating the time evolution of the charge packets induced by a horizontal ionizing particle impacting two adjacent drains. The collection efficiency is different for these two drains since their biasing state is different, reprinted with permission from Glorieux et al., copyright 2014, IEEE. Since the RWDD model has been implemented in an object-oriented language, C++, using dynamic containers, as previously explained in 3.1, complex circuits with an arbitrary number of sensitive areas and collecting nodes can be simulated, intrinsically considering, in this case, multiple node charge collection in the simulation process. The simulation begins with the initialization of the structure and the definition of the circuit nodes corresponding to the different simulated drains. In a second step, the electrical potential of each node is extracted from a steady-state circuit simulation. The values of these potentials are used to initialize the electrical field in the complete structure. Starting the time domain analysis, at each time step of the transient simulation, the magnitudes of the current sources corresponding to the different collection processes, simultaneously occurring at different circuit nodes, are updated as a function of the number of collected charge packets. Figure 4 illustrates this multiple node charge collection process in the simple case of two adjacent drain junctions. The time evolution of the charge packets induced by a horizontal ionizing particle in this two-node structure is shown at 5 different times after the ionizing particle impact. As evidenced in Figure 4, the collection efficiency of the two drains differs because they correspond to two different nodes in the circuit and their electrical potential, i.e., internal electric field, is not the same in this example.